Howdy! We're ready for Fundamental Chemistry 2, Chapter 17, which is on lipids and their functions in biochemical systems. Okay, so let's start our define lipids. Easy enough. So what are lipids? So lipids, the definition is always kind of tough, but we're really looking at a bunch of different compounds, ranging from fats to glycerides, non-glycerides. And so what we'll be looking at then is a range of compounds, and one of the biggest parts of this chapter will be learning how to categorize everything. All right, so as we go through these, I've got, oh man, a whole bunch of stuff on this. We got um, then what are the uses of lipids? And so, so we've got energy source. All right, we've got that energy storage, and so your body uses fats. It's built to burn fats. Burning sugar is kind of just an extra. So we get a lot of energy out of fat, and it's a great way of storing. So that's why you get fat when you store a bunch of energy. Our, we use these same lipids to build cell membranes, build hormones. We'll talk about vitamins a little bit. And then we use this both as protection for our body and insulation. All right, so let's start with the idea of fats. So fats really come down to whether it's saturated or unsaturated. So when I normally talk about a compound, we have said that a double bond is saturated. Well, what we're going to do here is we're going to ignore the carbonyl. So we ignore it, all right, and then everything else saturated. That means we're going to have no carbon-carbon double bonds, all right. So then we'll also deal with mono unsaturated, which means they have one double bond. Polyunsaturated, where they have more than one double bond. And then we have this idea of cis and trans. All right, so the way these fats are made in nature, they are 100% cis, 100%. So the problem is if we make things in lab, they tend to be trans by a large amount, well more than 50%. All right, so much more favorable for these long chain things to be packed in as trans, and so this causes us trouble because your saturated fats are going to be found in different places than your unsaturated fats. All right, and so your saturated fats have quite different uses. So let me click here. We'll skip. I'll let you read the biological processes in the book. But okay, so here's our saturated fats. So they line up, and what's great about those is they can line up close to each other, and so one can pack in right up against the next, and they pack in really nice and tight, and so they tend to be solids. All right, and so if they're solids, then that really helps out. We're looking at like animal fat. So when you get some bacon grease, it's a solid at room temperature. Then you heat it up a little bit, and it starts to melt and go back to liquid temperature, right? Room temperature. Now, if we get a mono unsaturated, then we can either have trans or cis. And so you can see if it's trans, it still packs in quite nice, but our body doesn't know what to do with it. And my body really can't do anything with it. It really struggles to do with it. And so trans unsaturated fats, really, really bad for you. And so when I look on this container here of vegetable oil, so it says total fat, and it lists saturated fat, polyunsaturated fat, monounsaturated fat. Now this one doesn't particularly list it, but quite a few others. So this is newer than some of my other containers of things, which would also go on to list trans fat. Now that trans fat should always read 0. It's been outlawed in most countries because of dietary concerns. All it does is cause bad health effects and no good health effects. So why might they use? Well, when I picked up this, I said it was mostly polyunsaturated fat, and so that meant it stays is this oil, right? So it's liquid at room temperature. And so it sometimes all those unsaturation points are also places where it can be attacked by bacteria and it can go bad, it can go rancid. And so if long-term storage, we would quite often hydrogenate it, or you might even see partially hydrogenated things. That's language they use with a lot of fats. And so it's really a matter of getting rid of these double bonds. So they're reducing them, adding hydrogens, adding two H's, right? But if they, when they're doing all this, um, if they happen to get any kind of trans fats, they were nice from the standpoint of your oils didn't go bad over time. They had a longer shelf life, but they were really, our body just didn't know what to do with them, all right? So when we look at these then, so we're not, the trans, we don't have to worry about now in our diet so much anymore. So the cis unsaturated fat, you can see it's got much more difficult time for these to line up next to each other. And because of this cis configuration, and if I have more, it's even worse, then they really have trouble getting close to each other. And so they don't pack in real tight. There's not a lot of attraction between intermolecular attraction, and so that means they stay liquids. All right. So what we expect to see then is saturated fats are going to be solids at room temperature. Monounsaturated fats will be more of a greasy oil, and so like a real thick viscous oil that quickly melts. And then polyunsaturated fats are going to be these liquids. So when I go look at a container of margarine, for instance, I'll see that it's got a lot of the same stuff, almost the exact same makeup. They just have slightly different amounts of polyunsaturated and monounsaturated. All right, and that's enough to make it into a nice, smooth, easy to spread uh, container. So they don't just use one fat anymore; they use mixtures. And then if I go in there and get a big stick of butter, it's much tougher. It's much harder. All right, and so even at room temperature, it's tough to cut compared to easy to spread margarine. Why? Because it's got a lot less unsaturation going on. Okay, so uh, there we go. So saturated will be solids, mono will be lower, someplace in the middle. They're not really liquids, but they're real easy to spread. Think of country crock or something like that. And then polyunsaturated will be liquids. All right, now how to name these things? Well, one of the keys to this, what these fats are, all they really are is just long chain, super long chain. Uh, so fatty acids, what they're called, and so they're just long chain acids. And so they're carboxylic acids. But the problem for us is this number of repeat units here. We number it 1 at the carboxylic acid. Well, it's not uncommon to have these things get up 16, 18 carbons before we learned how to go to 10. All right, so now we've got to learn how to deal with more than 10. So we use prefixes in front of decane. So decane is 10. Would be undecane would be 1 plus 10, and then dodecane would be 2 plus 10 would be 12. Tridecane, so it might sound like tridecane might be 30, but it's so that's why it gets they drop the decane after a while, so it's 1 plus 3, right? And so when we get to 19 nonadecane, that's going to be 19, and then at 20 it switches to this icosanoic. So I want you to memorize 1 through 19. All right, so we're going to be doing 1 through 19. So all right, so let's draw 1. And I lost count already. Oh well. And then we'll draw another one. Alright, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Alright, so 14, that's going to be tetra, and instead of decane, drop the E, add oic, and then acid. Tetradecanoic acid. Alright, a little bit of a glare today. Maybe the blue would be better. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Alright, now we've got an added problem of having an alkene. So you name the alkene and then you drop the E, add oic acid. So we're adding in, well, it's almost the same number of carbons, all right? So tetra, and instead of decane, it's decenoic. So it's got this E acid, and this is at 9, so, and it is a cis 9 tetradecanoic acid. All right, so the double bonds between 9 and 10. So this is our new part, adding these double bonds. For each double bond in IUPAC, you would have to give the number and whether it was cis and trans. Okay. So notice I got 14 for both of these. They're almost always going to be even number of carbons, and that's just has to do with the chemistry that's going on inside the biology that's going on. All right, and so the when this is made in nature, it's almost always an even number, and it is always going to be cis. All right. So name the alkene, drop the E. So here's this one, same kind of idea, and so you can recognize that it has this this E right there tells me that E is telling me it's got a double bond. All right. Now we also use the omega system, and you'll see the omega system. This symbol looks like a W. All right. So the omega system, when I come on here, sometimes they'll have it. Nope, not on this one. Nothing really says great for you. But when I go in there, I've got some omega 3 and omega 6 and omega 9 and all kinds of different things. So some of them are supposed to improve memory, some are supposed to improve your heart health. The 6s tend to do that. We use a lot of those unsaturated ones. Our body just doesn't make, and so we have to get them somewhere else, and we use them to make the linings on our nerve endings. So really important. And we saw that, especially if it's polyunsaturated or even monounsaturated, it could be tough. And a lot of times when these things are being taken apart, they're going to be taken apart from the end and not the carboxylic acid part. And so when we're classifying these, then this omega system, omega being the last letter, all right, and so we'll number them from the back. So 1, 2, 3, 4, 5. So this one would have been one you just wouldn't really see, but it'd be an omega-5 fatty acid. All right, and so even if it was unsaturated, polyunsaturated, so let's start with one here. So we want to do there. There. So if I do that, this would be an omega-3 and an omega-6. Now here's the problem. This one's trans, so it'd be bad for you. All right, so this omega system, you can classify them even if they're polyunsaturated. And so when you see something about it, say, hey, you should get some more omega-3 stuff. It'll help your memory. That's where what they're talking about. It's not really difficult. You just start at the end and you count the carbons. All right, and so so in this one we can see 1, 2, 3. It's an omega-3 fatty acid. So remember, alpha and beta and gamma all were down here, and they just start omega all the way at the end. And so it's always going to have this omega in front of, so it'd be this omega-3, and so that's its classification. All right, so we're ready for glycerides. Now glycerides, you're going to take this compound here, which is glycerol. Now, the way it's drawn there is a little bit troublesome. So when we look at glycerol, it's just OH, OH, OH. Easy enough, all right? So it's propane. It's got 3 alcohol groups on it, extremely water soluble. Typically, we'll see it drawn like this, so that we get all these kind of lined up. This is probably not how it really exists, but it makes everything easy to recognize. This is the structure you're looking for. So this is glycerol. And if we combine it and make an ester bond, we get a triglyceride, and it's going to have this characteristic I'm just going to draw tails out for this. It'll have this characteristic structure. So CH2, CH, CH2. All right. This is the part that we can identify whether it's a glyceride. So if it's a glyceride, it has that. All right. So it's got all these ester linkages. So we learned how to do these, a little bit of acid and acid catalyzed ester linkage, just like if we were making aspirin. All right. So this is these glycerides, great for storing energy, and so we use these in our body. Now, monoglycerides and diglycerides happen, but our body likes to make all 3, and so when I go, oh man, I'm putting on my winter fat, this is what you're putting on. All right. So let's then look at the next category. So if I'll give you a picture and ask what kind it is, you're looking for this structure, this CH2CH, CH2. All right. Now, phospholipids are also triglycerides. So here's my CH2, CH, CH2. There's my glycerol. All right. So it's a glyceride. But they've replaced, instead of having all carboxylic acids, one of them's got phosphorus. And so it's a glyceride with the phosphoric acid here. All right. Now, this part that's got this phosphoric acid is extremely polar. And so it's the head here. And so there's our nonpolar. It's got all these carbons and hydrogens. Very nonpolar, does not want to go into uh, water. So this is kind of like soap. All right. So we've got a polar head and a nonpolar head. And so you've studied this uh, in biology. And then there's another component to these. We also can classify these on whether they're charged or non-charged. Now, charged, all you're doing is you're looking for the presence of positives and negatives, all right? And so here we see this nitrogen here has a positive charge because it's got 4 bonds on it. So nitrogen with 4 bonds always has a positive charge. And so we get this highly charged thing. So phospholipids, we've got a phosphorus, right? And it's a glyceride. So it's got that. All right. So then things get a little bit tougher when we start doing the non-glycerides. They're not based off of glycerol. Race while we're talking about it. So we'll start with the sphingolipids, and they're a little bit tougher to identify. So they still got this polar head and non-polar, but they don't have the glycerin thing. The steroids will be easy once we talk about them, and then waxes are actually quite easy. Waxes are going to be ester groups, and they're just a long fatty acid with a long alcohol. All right, and so our body uses them any place it wants something that's not water soluble. All right. Okay, so let's look at steroids. Steroids have this characteristic 4-ring structure, and so you need to memorize this structure to recognize that something's a steroid. So if it has that structure, it's a steroid. That's what I'll be asking. I'm not asking you to memorize what the shape of cholesterol or estrogen. You just need to be able to see this ring structure. Now notice some of them have double bonds. This one's even aromatic, but they've got that characteristic ring structure. All right. So on the test, I'll give you some of these structures and I'll ask about it. Which one is a phospholipid? Which one is cholesterol? Or which one is a steroid? Which one is a sphingolipid? Then, so that one is going to have not going to have that CH2CH. CH2. All right, so we're ready for our complex liquids, lipids. So here we're mostly talking about LDL and HDL. All right, and so HDL is the good, healthy. Think of that as being the healthier. All right, and so that's the main thing I want you knowing is then that HDL is going to be the good cholesterol. When people talk about you should have good cholesterol versus LDL is the bad cholesterol. Now, those things really have to do, you still don't want like a whole lot of cholesterol, but what you end up finding is that if you get a bunch of the saturated lipids, that you end up greatly increasing this LDL. All right, so that's really what this chapter is going to be about. We'll do some naming. We're going to do a lot of, I'll draw a structure and you'll identify it, or you'll tell me if it's omega-3. You're going to classify it. And so, like I say, the steroids and the waxes are pretty straightforward. So you'll tell me what kind of lipid it is. All right? It's not too bad. I'll catch you on the next one.